Okay. So in the previous video, what we saw that something like this, M1, M2, M3, to make this voltage bias this voltage, and this was made VDS1, and we had this one more diode connected, and this voltage is connected here, and this voltage VGS4, this is 4M4, this is VGS3, so VGS4 was made equal to VGS3. Okay, and this voltage was VDS1, so by this way VDS2 is equal to VDS1. Okay, so what was the problem at that case? The problem was that here the minimum voltage V out minimum is equal to VOV3 plus VDS1, that is, which is VOV3 plus VGS1, which is VOV1 plus VTH VOV3. So minimum voltage is 2 over drive voltage, extra is VTH, so we want to eliminate this. Okay, so problem is this, that we don't want this VTH, we want this minimum one, V over drive voltage of 3 over drive voltage of 1 or 2 at this V out minimum. So for that, what we do in now previous, this was already there, VDS1, and we have tried to make VDS2 is equal to VDS1. Now what we will do, we will make this VDS2, this VDS2 is equal to VOV over drive voltage, and we will make this VDS1 is equal to over drive voltage of 2. Okay, so you see the difference. In current circuit designing, what we will do, we will make this VDS2 is equal to overdrive of 2. Okay, and we will make VDS1 is equal to overdrive of 2. By this way, VDS2 is equal to VDS1 is equal to VOV2, and is also equal to VOV1 because VGS1 is equal to VGS2 and VTH1 is equal to VTH2. So now we will see how we will do the designing of this by making the VDS2 fix is equal to VOV2, and we will make the change in the circuit such that VDS1 is equal to VDS2 is equal to VOV2. Okay, so let's see. Now, one of the way is, what is that? Okay, so one of the way is, let's say this is the previous basic circuit. Okay, and this is the voltage. Here I have made VOV fix VOV2, and this VB we will design the circuit such that this is VGS3 and this is VOV2. Okay, now before going to design the VB part, let's see the VDS part, because VDS should be equal to what? VDS should be equal to VDS1 should be equal to VDS1 2, and that is equal to VOV2, that is equal to VOV1, that is equal to VGS1 minus VTH. So VDS1 should be equal to VGS1 minus VTH, but Here in this circuit, VDS2 is equal to VGS2. So we need one more drop. Okay, here we need to make some changes. So what we do, we need one drop, extra drop from this to this. Okay, extra drop from this terminal here to here. So this is what the circuit is. So what is the circuit? This is the circuit. So what we did here, we have this VGS1, some drop, and this will become this is VDS1. So VGS1, some drop. What is that drop? Is the IREF multiplied by R1. This is the drop. And how and what we want, this drop should be equal to VTH1. By this method, we can say that VDS1 is equal to VGS1 minus VTH1, and that is equal to VOV1, which is equal to VDS2, that we have set to VOV2. Okay, and VGS2 is equal to VGS1. So this is the way to think that between these two terminal, from here we needed some drop from this terminal to this terminal, from 1 to 2 we need one drop, from this terminal to 2 terminal. So that is what we did by adding one extra R. So this is the trivial solution. Okay, so obviously if you make R, if you add R everywhere, it is mos, and you have added one R, so there will be some mismatch, or that will be because of the process voltage, temperature. And we can see that all, let's say this is PVT independent, this is drop will be PVT dependent, because R will be PVT dependent. Okay, and this drop should be equal to IREF R1 should be equal to VTH. So this two has to be equal, but it is not same for all the PVT corners. So there will be some mismatch. Okay, so this is the problem in this circuit. Now what is the solution? Solution is simple. We will remove this R and add one what? MOSFET, and see how the circuit will be. So just simple, we will replace this with a MOS. So what we will do, we will replace this with a MOS resistance, and here is the connection that was present between this and this, and between that there is a one resistance. We have removed this with a MOS. Now we want some voltage here, biasing voltage, such that this is equal to what? This voltage equal to VOV1 is equal to this VDS1 is equal to VOV1. Okay, then only it will be equal to this VOV2, VOV1. Okay, then this VDS is equal to this VDS, and above this we had VGS3. Okay, so we also want some voltage here, such that this is the overdrive voltage. This VDS is equal to overdrive voltage of the device, and this voltage will be VGS3. This VGS whatever 4 M4 should be equal to VGS3. So what we will do, we will connect this, but note that this is not volt, this VB has to be generated somewhere, because it is not generating at this point. Because to generate the VB we need something like this. Okay, because we have some current, we will have some current, from there we will generate some voltage from ground to node, something like this, something like this, some drop here, some drop here, total drop here will be generated here. But in this case, if you see, it is a terminal. Okay. Or what we can do, if this gate is connected here, then also this this will be generated. Some voltage will be generated. Okay. So we will see how we can generate this VB. Now, in this circuit, if you see, the solution is to replace this R with some MOSFET and bias this voltage gate terminal. Okay, so one of the thing is, why can't we make the circuit like this? Okay, so why can't we make the circuit like this, such that this is VOV2, which is equal to VOV1, this is VGS3, okay, and this is VOV1, we want to make it VOV1, and this we want to make it VGS3. Why can't we make this circuit like this? What is the problem? Because here also we can generate VB, because this is diode connected, and from this current we can generate this VB here and this is also diode connected. So think about it. We'll come to the circuit, we'll see. I'll add one more video on this, that what is the issue, or can we use this circuit as a current mirror. Okay, so but now let us see the what is the design. So design is simple, that we will replace this R with MOSFET. So this is the R, we will replace this with a MOSFET and need VB such that this is equal to this VGS3 is equal to VGS4 is equal to VGS3. So why we are making VGS4 is equal to VGS3? Let us see why we want to make this this thing should be equal to this. Let us see. So the circuit will be something like this. Okay, so what we did here, simply replacing the R and adding one MOS, and we will connect VB here. Okay, so if you see here, VDS1 will be VB minus VGS4, and this VB is also equal to VGS3 and VOV2. Okay, this VB is equal to this drop and this VOV, and this VB is also equal to VGS3 and this VOV. Okay, so by this way we will design such that VGS of 4 is equal to VGS of 3. Then we will make this VDS1 equal to VDS2, and from the beginning I was telling that VDS2 we have made equal to VOV2. So by this way we can generate this circuit, we can make this circuit such that this voltage VDS2 is equal to VOV2. Okay. Now, but problem is what? Problem is we need to generate this VB. What is the VB value? VB value is this drop plus VOV, or this drop plus VOV. This is VDS, which is equal to the VOV of this. Okay. Now the designing perspective is, with respect to design, we have to make this equal, this voltage equal, and VB also to be same as VB. Connection should be this two VGS has to be made equal, and because of VB is connected same between these two terminals, this voltage is forced, this VDS1 is forced to be equal to VOV VDS1, which is equal to VOV1 or which is equal to VOV2. Okay, this is being forced because of this VB, which is being generated from some other circuit. Okay, so this is the another way of making the current mirror. So where we were, so we have started with this circuit, basic current mirror, and we want this R out, V out to be VOV3 plus VOV2. So we have made this fix VOV2 some voltage based on this, what is the VGS and VOV requirement, and we want to make this change in VDS1. So that was the problem, and what we did, we have added one R in between these two terminals, such that VGS minus some drop becomes VDS, and that is VOV. And to replace this R, we have added one MOSFET, and that gate voltage is being connected to VB, that is being connected to both the terminals, such that this VDS1 is being forced to become VDS2, which was made VOV overdrive voltage of 2, which is equal to VGS1 minus VTH1. Okay, so this is the method. Okay, if you find something missing, let me know. Now, okay, some points from this. First is, okay, this is very simple, that okay, what is Cascode? We know this is input, and what is this? This is V bias, and this is output. This is basic Cascode circuit. Okay, so in this case, what we did, we have connected input to the output. So that is what mentioned here. So this circuit represents the Cascode connection between output and input, and this is also called as low voltage Cascode. Also, if you see this node, if you want to make this node connection here, then what will be the problem? Let's say if you connect here and use this circuit in the current mirror. Okay, connection here, and this is V bias. Let's say I connected this. Okay, so what is the problem? I'll generate VB from somewhere else. So problem is, this VDS is equal to VGS, and this VDS has to be equal to VDS2 equal to VDS1, which is equal to VGS1. Again, this is not equal to VOV, so we cannot connect this. So problem is, we cannot connect this. This is not better way. So better way is to connect here only. Okay, so this is justifying the circuit, that what is the connection between, where should we connect this, either here or here. So this is the way of thinking. Another point is, if you make these two devices, M4 and M1, in saturation, and this is already in saturation because we have to make this saturation and this diode connected, and this also M4 to be in saturation. If you solve the conditions, that is VDS should be greater than the VGS minus VT in both the cases, then you will find this. One of the important thing is that the overdrive voltage of this device, should be less than the VTH of this device. Okay, so VOV4 should be less than equal to VTH1. So our overdrive voltage of this should be less than VTH1 is the design perspective, design parameter, or you can say when you will design, you should be take care of this thing. So this is the few points regarding this circuit. So only thing is that we have to have VDS1 is equal to overdrive of 1, which is equal to VGS1 minus VTH1. So we cannot make diode connected, because then VDS1 equal to VDS2, VGS1. We don't want this. We want one more drop, VTH. For that we have added one resistance in between, and that drop is VTH, and then after that we replace this resistance with MOSFET, and then we have something like this. And this VB we have made such that whatever the right side circuit is, this is VOV, this is VOV, this is VGS3, and this is VGS3. We make this VGS4 VGS3. So this is the bottom line of this, how to design the circuit. Now going further, so in the previous circuit I mentioned that we needed this VB thing. Okay, we need this VB, this VB. So what is the value of VB? 1 VGS, 1 overdrive. Okay, so let's see how we will design this circuit. In the second circuit also the same, 1 VGS, 1 overdrive. So how we will design this circuit? Okay, let's see. So first is simple. You needed 1 VGS. What we needed? 1 VGS, this, and 1 VDS, 1 VOV. VDS is made equal to VOV. Okay, overdrive voltage, this VGS and VOV. So this I know means from basic thing, this VGS can be generated through the diode connected. So one diode connected you need, and extra drop you need. Okay, because here it is plus. So one extra drop and one diode connected. So how you will generate this? One diode connected, one extra drop, you will generate VB. So this is the very trivial thing, very basic thing. So only thing to be noticed here is that whatever the VGS here, this VGS5, VGS here should be equal to VGS3, this one. Okay, and whatever the drop here, okay, should be equal to overdrive. This overdrive should be equal to this, because one VGS and one drop is equal to one VGS here and one overdrive here. So one VGS, one drop, this should be equal to one overdrive. Okay, so what is the problem here then? This can't be the easy solution, means, so what is the issue here? So if you see here clearly, this has a body effect, because this bulk has to be connected to the ground, which cannot be connected to here. No? So this M3 has a body effect, and this M5, which is VGS, which VGS is equal to the VGS. So this does not have a body effect. So this can be one mismatching effect. Okay, Another problem is, if you see, this drop should be equal to VOV. Okay, so by this way, what is this VOV? VOV is VGS minus VTH1. And VTH1, where is the primary circuit? Where is the primary circuit? Let's see. This is the primary circuit. What we want? This VGS, this is the VGS minus this voltage. Okay, so this is IREF multiplied by R1. That is the primary circuit. We are creating VB voltage, this voltage VB. So in this VB we want VOB. So if you see clearly here, this VTH was equal to the reference into R1. So by this way you can see that your VGS1 is what? VGS1 is this. VGS1 is equal to this drop, whatever this drop, I reference R1, which was the primary circuit. If you go here, if you see here, this is the VGS, this is total VGS here, and this is the drop, and this is the VGS minus the drop. That is what we wanted. So when you compare this, the VGS is equal to 2 IREF R1 plus I6 R6. What is I6 R6? This is the VB circuit, the voltage generator circuit, where this drop I6 R6 is equal to VOV. Okay. Obviously, VGS is what? What is the VGS value? VGS is overdrive voltage plus VTH. And we know what is overdrive voltage we have created. Overdrive voltage we have created I6 R6. And what is the VTH from the previous circuit is equal to I reference and R1. So point is not the equation. Point is that here it is a PVT dependent. Okay. And here the variation is different, VGS. So this VGS and resistance drops will make the mismatch. So point is this. Point is not the equation. Point is that there will be a mismatch in the VGS value, or in the I6 R6, or in the I reference R1. They will not be same. The sum of two will not be same is equal to same as VGS. So there will be some difference. So this is the two problem. First is the body effect and second is this. So how we will solve this? Simply we will make, let's say what we will do, we will make this equation elaborate, and then we will see how we can generate this. So the second way is this way. So what we will do, we have elaborated this equation. What is the VB requirement? VB requirement is, if you see clearly, VB requirement is what? 1 VGS drop, 1 VOV drop. 1 VGS drop, 1 VOV drop. And this VGS is VGS VOV, VGS minus VT. So total is 2 diode drop and 1 out of 2 diode drops. 1 diode drop, 2 diode drop. 1 diode drop, 2 diode drop. Out of this 2, let's say this is the total diode drop. I want to have less, means not the extra one, but I want less VTH. So what is the way? So best way is, how we will do? Let's see. So if I connect, this is VGS1, this is let's say VGS1, VGS3, VGS1, and this will be total VGS1. I want to remove one drop. How I can do that? So another way is, if let's say if I connect here and I make one resistance here and I take this terminal, so what is the value? This value will be one VGS drop, another VGS drop, minus IR1. Okay, so what I did, I removed this connection from here, I connected here, and so now this will become two VGS, one VGS this and another VGS this, and added one resistance here. Now this voltage will become this voltage minus whatever the whatever I6, I7, whatever you make the current source, and from there drop will become this. So this is the way we can think about. Another way is can be possible is, earlier we have two diode connected, we can remove this and connect it here and then make this R. Will this work? What is the problem? We draw one drop, another drop, and what I make the change, I remove this here and connected this here and added one resistance and this terminal. So what is this? This is VGS1. Okay, and this is VGS1 minus IR. So this is not equal to the, what is the required value? Required value is 2 VGS drop. This is 1 VGS drop. So better way is not to take this but to take this. That's what. Let's see what is there. Okay, so see the same thing. So if you see here, same thing has been done. What was the requirement from the above? Two diode and one drop to be reduced, some voltage to be reduced from there. So method I mentioned before. So if you see this node, one drop, one VGS, two VGS. So this voltage is same here. So 2 VGS minus some drop. So this voltage will become VGS whatever 6, 2 VGS minus some drop, and we will make this VGS 6. What is this? To VGS 3. What is VGS 3? VGS 3 is nothing but this one, VB, the right side, VGS 3. This is VGS 3 and this is VOV. So this is equal to VGS1 minus VTH. So and here by this 2 VGS and 1 drop. So this VGS 5 will be make equal to VGS 1, and this drop IR6 we will make equal to VTH. Okay, and this VTH has to be equal to the VTH of the M1. And what is the VTH of M1? VTH of M1, if we see the primary circuit where we have designed, we made this I reference R1 is equal to VTH1. We made this circuit because then only this was VGS minus this VTH, this VDS will become the overdrive. Okay, so by this way, when we design this circuit for VB, we will just make it equal to IREF R1. Now this is the circuit design. Now what is the conclusion? How to design how to size the things, size the devices. So if you see clearly, I6 is equal to RF, reference current, whatever it was there, we have to make I6 should be equal to IRF, and R6 should be equal to R1. Then only the drop will be equal to the VTH1, and VGS5 should be equal to the VGS1. So from there, these two aspect ratio VGS5 and VGS1 means whatever the primary circuit VGS, this one VGS1, this has to be this size has to be made equal to 1. And if you see 6, how to this VGS has made equal to VGS6 has been made equal to VGS3 we know what is this is the VGS3, and from there we see that the sizing of sizing of M6 will be done according to this, because if we want same current then this is the method. So this is the sizing of the transistors. Method is simple, method is very simple. In a summary we can say that what we can say that we needed one VB is equal to VGS3. So there was one gate drop and one overdrive voltage. So this we can create one drop and one overdrive voltage through resistance. So this we can use as a VB. Okay. Another is, if we elaborate this, VB is some VOV is some VGS and VTH. We need two drop and we need two diode and one we have to reduce it by one drop. So one gate, another, but we need to have, this is 2 VGS, sorry, this is VGS3 plus VGS1, but we need VTH to in this voltage to be reduced by VTH. How we will do? We will add this another resistance here, and this voltage will be this total voltage. Okay. And this already I mentioned that why can't we connect this from here to here, because then this voltage will be equal to VGS1 and this voltage will be equal to VGS1 minus IR, which is not equal to the VOV, which is not equal to the VGS3 plus VOV2. So this is the method. So there are this is the two circuits to generate the VB voltage. So if you see clearly, this VB generation has been done for the case when there was resistance connection. So here also resistance connection, here also resistance. In this case this was the trivial solution where we have added resistance, and in this case we have added R for making equal to the VTH. If you see clearly, for the VTH we have added IR, I6 R6 is equal to VTH, and here it is I6 R6 is equal to VOV. So this is the method. Now when our primary circuit is being replaced, this R1 is replaced by the MOS, then we have to change the VB generation circuit also. This circuit, this circuit, this circuit, and this circuit. So this second one is better than the first one, obviously, because earlier these were the problems like getting body effect and the PVT process matching. So those has been removed in this circuit because we needed two diode drops and one VTH drop. So it is better than at least the above one. Okay. Now for the second circuit, if we go, what was the second circuit? This is the circuit where we have replaced R with the MOSFET. In that case, if we use, let's say if we use the previous this circuit for the VB generation, then what will be the issue? Issue is nothing. Here is the primary circuit. Okay, here is the primary circuit, main current mirror circuit. This voltage is to be connected to VB. So VB we need one VGS, one overdrive. Here also one VGS. Let's see what will be the issue. VB in this circuit, what is the VB will define? One VGS, one overdrive, which is VGS5, VGS6, this VGS6 plus VGS5 minus IR6. This is from the previous circuit. So from this what we see is here I6 R6 should be equal to VTH1, that we know from the previous, but in this case this has to be same. I6 R6 has to be same. In the previous what we saw is I6 R6 has to be equal to Iref R1. Okay, so problem is not in the VB generation circuit. Problem is not in this circuit. Problem is in this circuit here, that this R1 has a PVT dependency. But the VB generation circuit is made equal to the where is that? VB generation circuit has made equal to the, so here matching is happening. Now in our case here this is equal to VTH. So again PVT dependency. Okay. So circuit is simple. We needed one VGS drop and one overdrive drop. And this overdrive is 1 VGS minus VTH. Okay. Again now if we see closely, we want to replace this IR from a diode, from a MOSFET. Again we will replace this. Let's see how we can do that. So let's see what we did here. Here we have directly made the VB generation circuit. Let's see how. VB is this VGS, that is equal to VGS 6 is equal to VGS 4, VGS 3. Okay, and this voltage, whatever this voltage, is made equal to VOV1. Okay, so by this method this voltage will be equal to VGS 4 and VOV1 or VGS 3 plus VOV1. Okay, so we have removed that R thing. So what if you see clearly here, so basic thing is, let me draw it again. So basic thing is we have removed this R. So this is VGS, let's say 5 6, VGS 6 plus VGS 5 minus IR. Okay, and this voltage, we have removed this circuit, removed this resistance. Now the circuit is something like this. So what will happen, this drop will be 2 VGS, but we don't want this 2 VGS, we want one more extra. So if we connect this here, okay, then we have this 1 VGS and this is made, VDS has been made equal to VOV1 by designing. Okay, so you have to make by selecting the W by L such that this drop VDS1 VDS5 is equal to VOV1. So this is the way. So if you see clearly, this is the circuit for VB generation, and another way of connection is this. It seems like it is a stacked device, 5 and 6. Okay, so this is the way of generating VB So if I want to summarize this again, let's say if I want to summarize this, so this was my circuit. We have added R. Okay, we have added R here such that this voltage VD1 will be equal to overdrive voltage. Okay, VD1 equal to overdrive voltage, and to remove the effect of PVT from the R, we have replaced this R with the MOS. Okay, and this VD1 has been made equal to the overdrive voltage of the device. Okay, and the gate is connected to here such that both the two VGS are same. We will make by the designing. Now in these two cases, if we want to generate this VB also. For VB value of VGS and VOV, there are three methods. One is one VGS and VOV, one gate diode connected, one drop extra. So this is the way, one drop and one diode connected. Another way is, if you split this equation, then we need two diode voltages, and we have to reduce one voltage from there. For that, we have made the circuit like this, that this voltage is sum of these two voltage, and then this node voltage will be the drop of the VTH. And to remove the effect of R, here again we have one more circuit here where we have forcefully made this diode connected VGS to be equal to VGS6 is equal to VGS3, and this voltage VDS voltage had been made to overdrive voltage of the device. By this, the VB is forcefully made to VGS4 or VGS3 plus overdrive voltage, and then we will connect this VB to the previous circuits of the main current mirror here. Okay, so this is the way of designing the current mirror in the Cascode structure. If we summarize and if we see the different architecture possible, let's see what are they. So first is this. So we have made this, if you see, we have made this VOV and this is VGS. Okay, so this voltage is also VOV. How it made? This VGS minus some drop, so this has been made VOV. So this VOV and this both side overdrive has been made equal. Now, but we needed this bias voltage, and the bias voltage is a one gate drop and one overdrive voltage. So this is one gate drop, and this is IR drop, which is made equal to the overdrive voltage. Another way is to, when you will split this overdrive, we will get gate voltage reduced by the Thevenin. So one gate voltage reduced by the Thevenin IR drop will connect this. This is our VB. So this I already explained before. So there are two ways of generating VB through the resistor when we have one resistor here in the drop for the threshold voltage. Another way, when our circuit, primary current mirror circuit, the resistance is replaced by the MOS, and this both the gates are connected, and this VGS has been made equal to this, and this overdrive voltage is this drain voltage is made equal to the overdrive voltage of this. In this case we need this VB. So how we will generate this VB? Earlier we saw that there will be this two VGS and one IR drop that is equal to VTH. So this we will take as a VB. Another way is to have this VGS 1 VGS4 equal to 1 VGS drop and one overdrive drop through the MOSFET. So this is the connection. We cannot make this note that we cannot make this connection here, otherwise this will be equal to VGS. So we don't want this. So that is why we have connected this to here, such that this voltage will be equal to the, we will make this voltage forcefully to equal to V over drive voltage of 1. And obviously this VGS4 is equal to VTH1. Otherwise it won't be possible to generate VDS5 is equal to VOV1, because VDS5 is equal to VGS5 minus VTH1, which is equal to VGS5 minus VGS6 or VGS4 or VGS3, and this has to be equal to the VTH1. So this is the method of designing the circuit and based on the DC operating points. So this final summary is, we have two circuits, one with R, one with MOS, and in this case VB is generated through the resistance and drop, and when we split the equation we have this, and here when we have generated the VB through the above, these two are same. And another way is, forcefully we will make the circuit, we will design the circuit such that one drop is VGS and the other drop from the drain to source is equal to overdrive voltage. So that is the summary. Okay, thank you.